Hello guys, how are you doing? For today we're gonna try to see about liquid extraction. Liquid extraction can be carried out either in a single stage or multiple conducting stages. So for today we're gonna try to see about some basics during liquid extraction that we need to know about before doing some much about problems involving this mass transfer process. Okay, so liquid extraction, as I've said, is a mass transfer process since there is a transfer of solid from the liquid mixture we ordinarily have to the solvent added for the purpose of extraction. Okay, so liquid extraction have many application areas. So you can see, as you can see over here. And the next thing that I think good talk about is the advantage of liquid extraction over distillation. Okay, there are so many advantages that you can get by using liquid extraction rather than distillation. Okay, I've listed them out, but I just want to say about two of these things. And the first one is if we have a large amount of low boiling component in the mixture. Okay, we know in distillation separates the mixture first by boiling the low boiling point component. So if there is a large amount of this low boiling point component in our mixture, we're gonna need large amount of energy in order to separate the mixture. So by using liquid extraction, we can easily separate without the use of this large amount of energy. Okay, and the second point is that the formation of isotopes in distillation. As we know, in distillation, isotropic systems are formed, which limits the degree of separation. So these isotopic systems are systems which needs a special kind of distillation, which is what we call it isotropic distillation. And these isotopic systems are, for example, if we weld these systems, what we're gonna have is that we're gonna have the same composition as our original feed, or it means that the compound with low boiling point, which we want to distill it first, and the compound with high boiling point will boil at the same time, and so separation is not going to happen. This means that these isotopic systems cannot be separated by simple distillation. So in this case, liquid extraction is advantageous over distillation. The solvent should be ideal. The criterion for ideal solvents is listed out here, so you can check it as well. So single stage liquid extraction is used when the raffinate and the extract coming out of the first stage contains the desired compositions. Otherwise, a multiple contact stage is needed. When we come to the ternary phase diagram, it is designed to represent the composition of the three-component liquid mixture. Okay, an equilateral triangle is the most common, and it is just coming from the idea that if you take any point inside an equilateral triangle and measure and sum up the distance, the perpendicular distance from each side of the triangle, it will give us the attitude of the triangle, which in this case is the 100% composition of the mixture. The same is true for these ternary phase diagrams. If we take a mixture or a mixture of three components inside the ternary phase diagram, its composition will sum up to give 100% or one infraction. So when you see these ternary phase diagrams, there is a curve as shown here. This is known as the binaural equilibrium curve, which separates the two-phase region from the single-phase region. As we can see, this is the single-phase region in which the three components of the liquid mixture exist as a homogeneous phase, and this will be the two-phase region in which it is a region where the extract and the raffinate belongs. Okay, and this point is known as the plate point, which splits the binaural curve into the raffinate and extract phase, from which to the solvent side will be the extract, since the extract is solvent rich, and from which to the carrier side will be the raffinate. Since the raffinate is carrier rich, and these lines are known as tie lines. These are a set of lines which increase their slope in one direction. In this case, they have a negative slope, and this negative slope increases when you go from this to this side of the binodal curve. Okay, so these tie lines define the equilibrium that exists between the extract and the raffinates coming out of the same stage. Okay, for a single stage, since we have a single stage, our extract and raffinate will be in equilibrium, and so can be joined by a tie line. For multiple stage systems, the raffinate and the extracts in equilibrium will be from the same stage. So this means that if you have any mixture inside the binodal curve which is enclosed by the binodal curve, and if you have the tie line that passes through this mixture point, we will have an extract composition here and a raffinate composition here, which means that since the extract and raffinates are in equilibrium, they should be on the binodal equilibrium curve. So the extract, each and every tie lines in here represents the extract and the raffinate that are in the same stage. So we have single stage, and if we do a total material balance, F plus S, which will be our mixture M, which is A plus R. So if we do a component balance for A, component balance for A, which is the solute in this case, so the composition of the solute in the feed times by feed amount plus the composition of in the solvent times by solvent amount, which is the composition of the solute in the mixture times by the mixture amount. So our mixture will be F plus S. If we substitute XAF times by F plus XAS times by S, which is XAM times by F plus XAM times by S. So if we take a common F, which is XAF minus XAM, which is S into XAM minus XAS. So if you have the ratio F over S, which is XAM minus XAS over XAF minus XAM. So if you do the same component balance for the carrier C, balance, so the composition of C in the feed times by feed amount plus the composition of C in the solvent times by solvent amount will be the composition of the carrier in the mixture times by the mixture amount. So our mixture will be F plus S. So if we do the same thing for the ratio F over S, we will have XCM minus XCS over XCF minus XCM. Then if we equate these things and solve for XAM, XAM will be XAF minus XAS over XC at F minus XC at S times by XC at M, which plus XA at S times by XC at F minus XA at F times by XC at S over XC at F minus XC at S. So as we see this question, this can be written in the form of y, which is mx plus b straight line equation form. Okay, so if we have this XAM and XAM are the compositions of the mixture, the solute and the carrier in the mixture, and if we see the slope and the constant b all are the compositions which belongs to the solvent in the feed. So from this we can conclude that if we draw a line from F to S, which is the line Fs, our mixture M will lie on somewhere on that line. So if we do the same balance for the extract and the raffinate, which will be our mixture amount, the same straight line equation will come up. So this implies that if we draw the line between E and R, the mixture will lie on that line as well. So in most liquid extraction programs, in order to determine the extract and raffinate fluids as well as their compositions, we need to know where our mixing point exactly lies. So that is why we need to have a clue about the location of our mixing point. Don't forget to write your comments, and please share, like and subscribe if you do like it.